Okay, so welcome back to the weekly live sessions on mechanics and control of robotic manipulators. So until the previous week, we have been covering the topics until the mechanics part. Uh, I hope I'm audible. Yeah. So until next week, we have been covering the parts up to dynamic modeling of robotic manipulators. For this week, we'll be covering topics relating to uh, trajectory planning or how you want to plan a trajectory. If you want your robot to execute a specific motion, if you have a set of desired points, how can you plan a trajectory? And then we'll see various strategies used for planning trajectories in case of robotic manipulators. So, as before, like the first half of the session will be dedicated for a recall of all the concepts that we have discussed, and the remaining part will dedicated for solving some sample tutorial problems. So, basically, we'll start by the definition of the term called trajectory. So it says during robot motion, the robot controller is provided with a steady stream of goal positions and velocities to track. So in case for a typical robotic manipulator, you will have a ground fixed frame of reference, maybe x0, y0, and z0. And you may probably have an n degrees of freedom robotic manipulator, something, let's consider something generic like this. And you would be tasked to take this robot or this robotic manipulator through a series of a steady stream of goal positions and velocities to track. So maybe your initial robot position is probably somewhere around here. Maybe I'll call this as xi, initial position. And you will be tasked to take the robot through a series of positions. And you will finally end up with the robotic arm will finally end up at the final position xf, right? So on top of the initial position and the final position, you'll also be having a steady stream of intermediate positions as a function of time. So in a sense, in between your initial and final times, you'll also be having the velocities as well, because it's a function of time. You will be having a stream of velocities and stream of accelerations. So if you consider xi of t as your position, and f of t as your final position, you will be having all your intermediate positions. And on a similar manner, you will be also having your velocities, and you'll also be having your accelerations, right? So that your robot can track a series of points. And what you essentially do with this model is you will plug this model into your dynamic model. So if you can recall, your dynamic model would look something like this. Your torque at the generalized coordinates of a robot would look something like m of theta double dot plus n of theta dot. This is how your generalized, your dynamic model in generalized coordinates would look like. So what you would do is you would plug in the stream of trajectory coordinates into this dynamic model, as you will plug all these coordinates in terms of theta double dot, theta and theta dot, so that you can estimate the control input as a function of time. You will get this torque as a function of time, which is what you would be providing as inputs into these motors, right? So that is essentially why we need to have a trajectory planning, to have a steady stream of positions and velocities as a function of time. So this specification of a robot position as a function of time is called a trajectory. So the steady stream of all the positions, velocities, and acceleration as a function of time, we call them collectively as the trajectory of a robotic manipulator. All right. So In other words, trajectory is nothing but the time history of position, velocity, and acceleration of the end effector or actuator joints. So there are multiple ways in which you can define a trajectory. So, for example, in case of a standard 2R robot, maybe I'll label these coordinates as x0 and y0. You will have a 2R robot with two joints. Label this as R1, R2, and this be the end effector. So basically, there are two joint coordinates or two joint variables, theta1, and maybe I'll consider this to be theta2. So theta1 and theta2 are essentially the joint variables. And at the Cartesian coordinates at the tip of the end effector, we call x and y Cartesian coordinates. We can consider them to be the task space variables. And what we have over here at the joints are nothing but the joint space variables. So like we can either define the trajectory in terms of task space variables or in terms of joint space variables, right? For example, in terms of an inverse kinematic problem, you begin from an initial position x and xi and yi, and you want to reach a final position. Maybe I'll call this as xf and yf, right? And you want to plan a trajectory starting from an initial position and end up at the final position. So using some trajectory planner, you will generate a stream of intermediate positions and velocities. And then using inverse kinematics, you will obtain the corresponding joint variables, theta1 as a function of time, theta2 as a function of time. And that would be your inputs to the motors. In a different scenario, you can also plan the trajectory in joint space itself, right? So instead of planning trajectory in x and y coordinates, you can directly plan the trajectory in theta1 or theta2. So that will give a different sort of a trajectory. It will look different. Even though the initial and final positions are the same, depending upon which coordinates you are planning the trajectory, the motion of the end effector through the intermediate points would look different. So we'll see all these different aspects at a later point of time. But then we'll start this session by familiarizing ourselves or revising ourselves with different schemes of trajectory planning. So the first one over here is something called a straight line interpolation. Right, this is the simplest interpolation or a simplest trajectory interpolation that we can have. So basically, if you have an initial position x0 and a final position xf, what you essentially do is you simply draw a straight line, or you simply derive an expression of a straight line, and all these intermediate positions and velocities would be governed by the equation of a straight line, right? So here you can consider your independent variable as the time axis, right? And your dependent variable as the x-axis, maybe the coordinate that you're considering, x coordinate. And what you have over here is nothing but the equation of a straight line. We are familiar with the standard equation of a straight line, like y minus y0 would be y2 minus y1 by x2 minus x1 multiplied by x minus x0. Or if I take this y0 to the other side, you will end up with an equation something like this: y0 plus some equation something like this, where this term y2 minus y1 by x2 minus x1, this term over here would be the slope of this entire line. So this can also be further reduced into y would be m multiplied by x minus x0 plus some intercept c, y-intercept c. So exactly similar to that principles, we have this equation of a straight line, but in this case, your dependent variable is x and your independent variable is the time axis. So at any time t, you can essentially find the value of this variable at any time t using this expression x0, which is the initial position, plus xf minus x0 by final time minus initial time. This part would essentially be the slope of your straight line multiplied by t minus t0. So for at any time t, you will be able to obtain the expression for this joint variable x. So for example, if you have a single degree of freedom, robotic, you don't even have to call it a robotica, but an arm with just a single degrees of freedom, maybe theta, and it begins at an initial time, it will be theta I, at time t equal to t0, and at the final time, it will be at theta f, like time t equal to tf. And if you want to plan a trajectory, if you want to fit a straight line trajectory, you can use an equation similar to this. But then let's have a look at the velocities and accelerations for a straight line trajectory. So here, the position itself is a linear equation in time, right? It's proportional to the time. So if you take the derivative of this position, so x dot of t would look something like xf minus x0 by tf minus t0. It'll be basically a constant, for whatever be the time, your velocity would look something like a constant. Or in essence, if you take a derivative of a linear equation, its derivative would be a constant, right? So if you plot the velocity along the time axis, the curve of velocity would look something like this. This will be your velocity. So if you have a constant velocity throughout, the acceleration in that case, the derivative of a constant velocity, acceleration would be zero throughout, right? It will be basically zero. But in reality, since you have an instantaneous velocity at time t equal to zero, you will have an infinite acceleration just right at the beginning, and you'll also have instantaneous deceleration right at the end. But throughout everywhere else, you will be having zero acceleration. You'll have no control over your acceleration. But these are the specific features. If you try to use trajectory, the motion at the beginning will be very jerky. It'll be due to the fact that from the time zero onwards, you will have at the initial time itself, you have a sudden instantaneous velocities, and at the end time, the velocity suddenly or instantaneously drop to zero. Your acceleration would be infinite, at the initial time and at the final time. But it will be zero, it will immediately come back to zero at, between the initial and final time. So these are the characteristic features of a straight line interpolation. And we probably won't be using that much, because of these issues, instantaneous accelerations at the beginning and at the end. So to counter these issues, we go with smoother trajectory generation. So over here, we basically have something called a cubic interpolation. So instead of interpolating a straight line between an initial position and a final position, instead of a straight line, something like this, we would be having a smooth third order curve, something like this, so that it will have it will gradually it will start from the zero position, and its velocity would increase gradually. It will stabilize at some point, and as it nears its final position, it gradually slows down. Right. So you can write a third order polynomial, or you can write a third order trajectory in this generic form. A0 plus A1 multiplied by t minus t0 plus A2 multiplied by t minus t0 square plus A3 multiplied by t minus t0 cube. So at any time t, you will be able to find the position t. If you are given x0 and xf, At any time t, you will be able to find the corresponding x coordinates using this governing equation. So in most of our applications, we consider t0 as 0. We essentially, it's very convenient to shift the origin uh, at time t equal to 0, where our trajectory is actually starting. So in most cases, we'll consider t as 0. So your equation would, the general equation would look something like this. X of t would be a0 plus a1t plus a2t square plus a3t cube. And if you consider the velocities, if you take the derivative of this equation, it would look something like a1 plus 2a2t plus 3a3t square. And you should also notice that the generic equation has four constants. You have a0, a1, a2, and a3, which is essentially unknown for the at the time being. So how do we find out these coefficients a0, a1, a2, and a3? You will be able to find these coefficients using the boundary conditions given to you in the form of initial position, initial velocities, final position, and final velocities. So if you are given an initial position, maybe x at time at 0, sorry. If you consider your initial position x at time t equal to 0 as x0, and at time t equal to tf, maybe a final time, if you consider your final position as xf, and two more initial conditions in terms of velocities, x dot at t equal to 0 as x0 dot, and x dot at t equal to tf as xf dot. You can basically write four equations using these boundary conditions. From these two generic equations, you can essentially write four equations. So that would look something like, if you substitute t equal to 0 in both of these equations, it would look something like x0 would be a0, and x0 dot would be, if I substitute t equal to 0, you'll get a1. Then xf would be a0 plus a1tf plus a2tf square plus a3tf cube. And xf dot would look something like a1 plus 2a2tf plus 3a3tf square. So you basically have four equations. x0, x0 dot, xf, and xf dot would be your boundary conditions that will be given to you, because that is what you really want to achieve. You want to plan a trajectory from an initial position and initial velocity to a final position and final velocity. So you will have, you will be having a desired boundary conditions, and you will also be knowing your time duration, TF, the time for executing this entire trajectory. Right? That'll be also your choice. Whether you want a faster time or whether you want a slower time, that is also your choice. So the only unknowns that you have in the system of four linear equations are essentially A0, A1, A2, and A3. So basically, you can solve these four equations in four unknowns simultaneously to obtain the values of these coefficients. So that will look something like this. You can write this in terms of a matrix and a vector form as something like A0, A1, A2, A3, and your matrix of coefficients would look something like maybe 1, 0, 0, 0, then 0, probably 1, 0, 0, then 1, TF, tf square, tf cube, then 0, 1, 2 tf, 3 tf square. And on the other side of your equality, you have x0 dot, xf dot. So this is of the form a multiplied by x equals b. So you can find these unknowns a0, a1, a2, a3 as x would be a inverse multiplied by b. So if you invert the matrix of coefficients and you multiply that with your your vector of boundary conditions, you will be able to obtain the value for this constant, the coefficients of the polynomial. So once you substitute the values of these polynomials into the actual trajectory, you will be able to find out the numerical value of the corresponding variable at any time t. So we'll see that while we are solving some problems. That is how the trajectory is generated using a cubic polynomial. Due to the fact that the cubic polynomial has a degree 3, if you take the derivative of the position coordinates or the position variable, your velocity profile would look something like this. Maybe at the middle of the trajectory, you will have the maximum velocity. So for a cubic polynomial, you will have a parabolic velocity profile. And if you again differentiate your velocity profile with respect to time, you will get the profile for acceleration, which would be linear, right? If you derivate a second order polynomial with the time, you will have a linear, you'll basically have a linear equation for an acceleration. So in this case, you can have an depending upon your boundary condition, you can have 0 velocities at the initial and final end, or maybe according to your boundary condition, you can have non-zero velocities. But then here you can see at time t equal to 0, you will have a sudden acceleration. It's not infinite, but there is a sudden jump over here. When it gradually drops, it will be 0 at the midpoint, where the velocity is more or less peak. You will have 0 acceleration, and then you will have negative acceleration all the way to the final time, and then suddenly it drops back to 0. You can have control over velocities, but the initial acceleration, whatever you have over here, you won't be having any control. That will come out as a constant. And also due to the fact that this is a cubic polynomial, you only have 4 coefficients. As a result, you can only have 4 boundary conditions, which is, two 4 positions and 2 4 velocities, at initial and final points. But then you don't have any control over accelerations. You have no boundary, you have no control over accelerations. So whatever you get here is entirely dependent on your initial position, your final position, and the time you take to achieve this trajectory. So, if the time for realizing this trajectory is more, maybe this jump in this acceleration would probably drop. If it takes more time, this drop would somehow reduce. But if the time is actually very short, that demands for a very steep acceleration, something like, something very similar to a steeper curve. So it's more or less somewhat better compared to the straight line interpolation, right? In straight line interpolation, we had an infinite acceleration at the beginning and at the end. But here, in case of a cubic polynomial, we have a finite acceleration, not infinite. Even though there is an instantaneous jump, it's still finite, not infinite in case of, as in the case for linear systems. So yeah, this is what we have covered. In the particular situation, when we consider the velocities, the boundary velocities as 0, and if you consider time initial time as 0 as well, you can end up with an analytical expression for all the coefficients. So A0 would look something like x0. A1 is always going to be constant. A2 would look something like this, or you can write something like 3 by tf square xf minus x0. And A3 would look something like my 2 by tf cube xf minus x0. So your trajectory x of t would look something like x0 plus a1 is 0, then a2 you will have 3 by tf square xf minus x0 multiplied by t square plus, or it's minus I rather, minus 2 by tf cube xf minus x0 t cube. So you can directly use this analytical expression provided the initial velocities x dot at time t equal to 0 is 0 and x dot at t equal to tf is also 0. In this particular case, you can directly use this expression. Otherwise, you will have to substitute in the corresponding values and then find the inverse of this coefficient matrix and multiply it with whatever boundary conditions that you have. That's one way to do that. All right. Now, as I was saying earlier, you can essentially have a look at the position, velocity, and acceleration profiles. For the position profile, you begin with an initial position. Maybe this would be xi at time t equal to 0, and this would be your final position, time t equal to tf. The position would be xf. And this is a third order polynomial. The curve is actually governed by a third order polynomial. And the velocities, which is essentially the derivative of this third order polynomial, this will be a parabolic curve. And acceleration, which would be a first order. If you take the derivative of the velocities, you will get a first order curve, something like this. And the initial value, the initial offset that you have, the sudden offset that you have over here, is nothing but 6 by tf square. So if you substitute these initial conditions into this expression and take the derivative of, if you take the derivative of the terms, and if you substitute at time t equal to 0, you will end up with this expression, 6 by tf square. Right? So that is what this intercept is, or that initial offset is. And if you again do the same thing, if you take the derivative of this position, and if you try to find out the velocity, the maximum velocity, then you will be able to get this expression, the expression for maximum velocity. So as you can actually see, the maximum velocity occurs at time t equals tf by 2, and that is also where you have 0 acceleration. This will be time t equal to tf by 2. So if you substitute time tf by 2, into the velocity expression, you will be able to get maximum velocity as 3 by 2 tf. But if you substitute time t equal to 0, in case of acceleration, you will be able to get this term 6 by tf square. If you want to find out how much would be the initial sudden acceleration in terms of a cubic trajectory. So then let's see another case where we have something called a cubic trajectory with via points. So earlier, in this case, we have considered the case where you have an initial position xi, you will have an initial velocity x dot I, and you will have a final position over here xf, and you will also have a final velocity xf dot. So maybe I'll depict this as the points. So we have also seen how to generate a trajectory between these two positions having these two velocities. But then what happens if there are not just 2 points, but there are series of such points? Maybe you have one more point over here, another point over here, another point over here, another point over here in the robot's workspace. So now in that case, if you have several such points, you will have one initial point and you will have one final point over here, xf and xf dot. And all these intermediate points are called via points. So essentially, you want your robot to pass through all these points and then reach this final position, actually. Uh, if you plan a trajectory with just the initial and the final position, it will look something like this. But then if you want to, if you want your robot to pass through all these intermediate points, you will have to plan trajectories between these sections, maybe a cubic trajectory between the initial point and the first via point xv1 and the second via point xv2, the third via point xv3 and xv4. So you'll essentially will have to plan trajectory between either of this, all of these sections. This would be the first trajectory. This would be your second trajectory. This would be your third, fourth, fifth, so on and so forth. If you do the trajectory planning only between the first and last coordinates, it would look something like this, just ignoring all the other intermediate points. So this can be done using two different cases, right? Two different cases that are, in the first case, the velocities of k via points are specified. So apart from their positions, you will specify their velocities xv1 dot, then xv2 dot, xv3 dot, xv4 dot. So that will be specified. And then in case 2, the velocities of the k via points are not specified. So the velocities would be specified at the initial point and the final point. All the intermediate velocities of the via points are not specified. Only their velocity, only their positions are specified. So these two cases, have different implications on the trajectory that is planned. For the first case, in case if the velocity of k via points are specified, what we have to do is we only have to repeat whatever we have done earlier. We basically derived the the system of equations of the form ax equal to b, and then we find the coefficient x as a inverse b. We only have to repeat that between each of these individual sections. Just repeat it, find out the coefficients, and when the robot is in a corresponding, when the robot is in a particular section, use the equations for that particular section. So what we have to do is we only have to replicate whatever we have done in multiple number of times. When the via point velocities are specified, but in the case where velocities are not specified, what we basically do is we consider the final velocity of the first segment to be the initial velocity of the second segment, and final velocity of the second segment would be considered as the initial velocity of the third segment, so on and so forth. We'll enforce further constraints, additional constraints, so that it will be interconnected, right? Maybe, if you have a trajectory like this, the final velocity of this first segment would be the initial velocities of the second segment. And it will basically get carried over and over. But then in case one, we'll have the velocity specified as per our own demand. That's the only difference. So let's look at the implications. What implications do we have? So if the velocities are specified, you essentially plan two independent trajectories. Maybe I'll call this as section 1 and section 2. So as you can see, you basically have two independent trajectories. So the first section would be governed by maybe theta of t would be a0 plus a1t plus a2t square plus a3 t cube. And the second section would be would be governed by another equation. Maybe theta of t would be b0 plus b1t plus b2t square plus b3 t cube. It'll be essentially be completely independent. And in that case, your velocities would look something like this. If you take the derivative of this would look something like this. And if you take the derivative of this curve, the corresponding velocity would look something like this. And if you take the derivative again for accelerations, your acceleration profile would look something like this. Initially it'll be a linear with a specific slope and with a specific offset. And for the second part, you will also have a linear segment, but now you will have a different offset because this is an entirely independent trajectory. And at the via point, you can actually see that there is a discontinuity in acceleration. From this point, you will have a sudden jump to a higher value, then it linearly decreases to the final value. So this is the implication, the effect when you specify the velocities of the via point, you end up making the accelerations discontinuous at the via point. So, once it has reached the via point, there will be a sudden jump in acceleration because of this instantaneous peak at this location. So as it passes through the via points, it will have some jerks or it will have some wild accelerations in case when the via point velocities are specified. All right, that is the implication when via point velocities are specified. But when via point velocities are not specified, so in the first, we basically solve a set of multiple number of equations, but there will be certain constraints. There will be some more variables which are solved by further constraints considering x1 f dot would be x2 I dot. You will have further constraints as well. So the final velocity of the first segment would be constrained to be the initial velocity of the second segment. Considering we only have two segments. We only have a via point between the initial and final time. So if you consider this to be the first segment, this to be the second segment, this constraint would essentially bring some coupling with the two sections. And in that regard, you can actually see that the velocity is now looking more continuous, right? Compared to the earlier case, like you have a sharp, maybe a discontinuity at this location. But when the via points velocities are not specified, it looks like a very smooth curve. And as a result, if you again take the derivative of velocities, you will have positions. So the first segment would be a linear with one slope. Second segment would also be linear with a different slope. But then here you can see that there is no sudden jump in acceleration. There is a discontinuity over here, but it's not as drastic as the previous case. Not really as drastic. It's still connected, actually. So those are the two cases, or those are the two behaviors you can expect when when the velocities of the wire point are specified and velocities of wire points are not specified. So naturally, the trajectory of your robotic arm would be more smoother in case when only the locations are specified, but not the velocities of the wire point are specified. All right, so that's about the case of wire points. So similarly, like how it just as in the case of third order polynomial, we can use higher order polynomials. Maybe we can use a fifth order polynomials. So a fifth order polynomials would look something like this. Theta of t would be a0 plus a1t plus a2t square plus a3 t cube plus a4 t to the power 4 plus a5 t to the power 5. And here you can see that there are actually 6 coefficients, 1, 2, 3, 4, 5, 6. And due to the fact that we have 6 coefficients, we require 6 boundary conditions to solve for these constant coefficients, which can be your initial positions, x0, initial velocities, x0 dot, initial accelerations, x0 double dot, and your final position, xf, final velocities, xf dot, and final acceleration, xf double dot. So if you have a requirement of satisfying initial position, velocity, and acceleration, and the requirement of satisfying final position, velocity, and acceleration, you can use a quintic polynomial. So in that case, your position would be a fifth order polynomial. So it will look something like this. So theta of t versus t, this would be a fifth order. Oh, I think it will look something like this. This is essentially a fifth order polynomial. And your velocities would look something like this. Theta dot of t would look something like this. This would be a fourth order polynomial. So according to your boundary condition, you can have an initial velocity. Here I have depicted it to be 0, but it can be as per how you define your boundary conditions. And your accelerations, therefore, would become a third order polynomial, something like this. This would be a third order polynomial. This will be a theta double dot of t. So unlike the case of a cubic polynomial, in case of quintic polynomials with fifth order polynomial, you can have control over initial positions and final position. You can have control over initial velocity and final velocity. You can also have control over initial acceleration and final acceleration. There won't be any jumps. So here you can see that even velocities is very smooth, even acceleration is also very smooth. Earlier, it was linear throughout the time frame, except at the beginning and end, where it will suddenly jump to a finite value. But here, in case of quintic polynomial or fifth order polynomial, you can see that even acceleration is also very smooth. There is no sudden jump at initial time. Right? So if you want a very smooth trajectory, if you want to guide your robotic arm from an initial position to a final position using a very smooth trajectory, you can plan a trajectory using this fifth order polynomial. But then again, the computational costs will be obviously higher compared to a third order polynomial or a straight line interpolation. But in that case, you will have to make a compromise, between the smoothness of your trajectory or your computational time, which is of depending upon your priority. You can either choose to sacrifice computational speed for smoother trajectory or sacrifice smoothness for higher computational speeds. All right. So that is about higher order polynomial trajectory planning. So in a similar manner, what we did with um, a third order polynomial, we can also solve. We can also solve for these six coefficients using six boundary conditions. So the first three are position, velocity, and acceleration boundary conditions at time t equal to t0. And these are basically the final boundary conditions for positions, velocities, and acceleration at time t equal to tf. So if you substitute the value of t0 and all these values into this equation, you will basically end up with the equation of six system of six equations having six unknowns. So these will be your six unknowns. So you will be able to reduce this as a matrix and vector form, and if you solve those six equations, you will be able to obtain these coefficients. So the principle is exactly same as how we did it for a cubic polynomial. Yeah, so the corresponding coefficient matrix would look something like this. This would be your A matrix, where this TF over here would be your time duration, your total duration for your trajectory planning. And these are your unknown coefficients. And here, the vector here is essentially your boundary, conditions. So the first term is initial position. And in this example, we consider initial position and initial velocity and acceleration to be 0. And the fourth entry would be our final position. And the remaining two entries are final velocities and final accelerations. So typically, even in a practical case, we prefer to have initial velocity and initial acceleration to be 0, as we have, uh, you know, expressed over here. And we also prefer to have our final velocities and accelerations to be 0, right? We begin from rest, we gradually increase our velocities and acceleration. And as we reach our final position, we slow down. And once we reach the final position, our velocities and accelerations would be 0, right? So this would be a very good representation of what we are implementing in the practical case, because we really don't want a non-zero velocity and acceleration, right? We don't want our robotic arm to have a sudden instantaneous velocities at time t equal to 0, right? It's only natural for the robotic arm to start from rest, gradually pick up its speed, and as it nears its goal point, it gradually decreases. So these boundary conditions are pretty much realistic over here. All right. So we have covered fifth order polynomial trajectory planning. Yeah. So just like what we did earlier, these are the position, velocity, and acceleration profiles for a quintic polynomial. So the first one over here is the profile for position. This is actually a fifth order polynomial. And your velocity profile, if you take the derivative of a fifth order polynomial, you will get a fourth order polynomial, fourth order polynomial. So here, this will also be a very smooth curve. And the maximum velocity, the peak velocity that you can have is given by this expression 15 by 4 TF square. And the time that this maximum velocity would occur would be this TF by 2. It's easy to verify that on our own. And the acceleration profile would be a third order polynomial, would be governed by a third order polynomial. And the maximum acceleration is obtained as 20 by t square root 3. We have zero acceleration at TF by 2, and we have maximum accelerations at TF by 4, and maybe over here 3 TF by 4. We'll have a minimum acceleration or negative acceleration at time 3 equal to TF by 4. But here also you can see that the acceleration is also very smooth. It begins from 0 and it also ends at 0. So it follows a third order polynomial, which is very smooth. So these have very desirable properties compared to the earlier considered cubic polynomial or even the straight line interpolation, which has infinite acceleration at the very end and at very end and also at the very beginning. So the only drawback is the computational cost would be much higher in case of a quintic polynomial compared to the other two cases. So it's always a compromise, whether you want a smoother trajectory or you want less computational time. So depending upon your priority, you can choose between any of these cases. Another scheme is something what we call as a straight line interpolation with parabolic blends. So, if you plan a trajectory just with a straight line, we have already seen this earlier, right? If you have an initial time t0 and if you have a final time vf, and if you have an initial position xi, and if you have a final position xf, if you plan a straight line throughout, from initial time to final time, your velocity profile would look something like this. It'll be a constant, but it'll have a jump. It'll have instantaneous jump to that constant value at initial time, and an instantaneous drop to 0 at final time. And your acceleration would be 0 throughout. But then at the very beginning, you will have infinite acceleration and infinite deceleration at the very end, due to that instantaneous jump in velocity. So what we do in this case for a straight line with parabolic blends is, we try to focus on these problematic areas. Everywhere else, we simply follow straight line. But during that problematic area, right at the beginning and right at the end of the trajectory, what we do is we basically blend the trajectory with some parabolic curve. So maybe I'll call this as time t equal to t0. This would be the blending time t equal to tb. And there will also be one more blending time. Okay, I think somehow suddenly the meeting got terminated. I'm not sure why. I hope I'm still audible. I got a message that I was not able to see. Okay, I hope I'm still audible.
Yes, audible, sir.
Okay, thank you. Okay, so where were we? Yeah, we were. I said we were focusing on this problematic region where we have sudden velocities and sudden acceleration. So what we do is we have these two regions, what we call as this blending zones. I'll also call this as time t as blending for the final part. So initially, as we begin from 0 all the way to this blending time, we'll have a second order curve. We plan the trajectory to follow a parabolic curve like this. So this would be, a second order curve, something like this. And in the middle part, we have a straight line over here. This would be a straight line. And from the final blending point, we blend a smooth second order curve until it reaches the end point. So this would also be a second order curve, right? So depending upon your preference on this blending time, either this blending can be very gradual, or it can be very sharp, or it can be very smooth and very gradual. If you consider the velocity profile uh, for this blending period, this is second order curve, and your velocity would be a first order curve actually. Since this is of order two, your line would be of first order. It will have a constant slope, and from this initial blending to the final blending time, you have a straight line, right? You have a curve of order one. So the velocity would be of order zero, right? If you take the derivative of a line with order one or with dd1, your velocities would be zero. And from this point onwards to your final position, it will again follow second order curve. So again, your velocities would be you would be having a linear profile, something like this. So earlier it was constant throughout. In case of a full straight line or straight line trajectory throughout, it would have been something like, from zero, it will jump instantaneously. It will be constant until it reaches the final time. Then it suddenly drops back, something like this. But due to the fact that we are blending a parabolic curve at the beginning and at the end, velocities would be now varying linearly, at the blending during the blending period. Like so, it will be constant and it will gradually decrease to TF. And in a similar manner, you will, instead of infinite accelerations at the beginning and at the end, you will have a constant acceleration at the beginning. Then it will drop down to zero, and then during the final blending, it will again have a negative acceleration, and it will drop. So this period was identical to the case where we considered a throughout straight line trajectory. But due to the fact that we are having these blends, instead of an instantaneous velocity, we have a gradual increase to the velocities. And instead of an infinite acceleration at the beginning, we have a finite value of instantaneous acceleration at the beginning, and instantaneous deceleration at the very end. Everywhere else, it's zero throughout. So in that manner, this straight line interpolation with parabolic blends in some way better compared to a straight line interpolation throughout, right? Because of that infinite acceleration and all those things. All those problems are somehow managed when we introduce this parabolic blends at the beginning of the trajectory and at the end of the trajectory. So that's about the trajectory planning using straight line, but with blends, parabolic blends at the beginning of the trajectory and at the end of the trajectory. Everywhere else, it's linear. It's a straight line in time. All right. So one more case of trajectory planning would be something called a trajectory as per the cycloidal motion. Similar to how the profile of how we generate a cycloid. So typically, let's see what a cycloid is. So if you have a straight line, and if you roll a circle over a straight line, maybe if you consider this to be the circle, the locus of a point, locus of any point on the circle, uh, the locus of this point on the circle, as the circle rolls on the straight line, is what we call as the cycloidal motion. So, like for example, if you consider this to be the point whose locus is what we are tracking, And if you consider at initial time, the circle is at this location. And as time progresses, the circle would roll to a different location. It rolls without slipping. So now the new location of this initial point will be somewhere around here. And at a different instance, at a different time, it would be somewhere around here. And maybe at a different instance, it would be somewhere around here. So if you consider the locus of this point as the circle rolls, one full revolution over the straight line, the curve would look something like this. It would look something. The locus would look something like this. Something like this as the circle rolls. So if you plan a trajectory as per how this curve moves over time, that is essentially what we call as the cycloidal motion. So now we have to write a governing equation based on how the position of this point or the position of this point changes with respect to time. So if we can write a governing equation for this point as time varies, that equation would be the trajectory. That equation would essentially give you the trajectory information uh, regarding that variable that we are interested to find. So let's see how to derive that. It's not a complicated problem. It's fairly straightforward. So let's consider this point. Maybe this point of interest. So maybe at initial time, maybe at xi, I'll consider the time as ti, or maybe ti as 0. We'll always consider the initial starting point as 0, and then we displace this circle, or we let the circle roll by a finite angle alpha. Now, maybe at some other arbitrary location, this point, as the circle rolls, will go to a different location. This was the initial location, and I'll consider this angle to be alpha, right? So how do we write this governing equation of this equation? So if you project the locus of all these points into your x-axis, initially it will be at an initial point xi. So your x of t would be xi plus you want to account for this distance, probably this distance, that is the x distance that it has moved. As the circle rotates by an amount alpha, this point has moved this much distance, So how much would that distance be? We have to calculate, or we have to compute this distance. So how do we do that? So we basically know that for one full rotation of the circle, it moves a distance of 2 pi radians. So the circumference would be 2 pi r, right? So for one full rotation, the distance moved by this point xi uh, r multiplied by 2 pi, or 2 pi r, which is essentially the circumference. But what about at some intermediate rotation? No, if it rotates full rotation, that is 2 pi radians, it'll move by an amount of 2 pi r. But what if it moves a finite radian, not 2 pi, but just an alpha radian? This entire distance, would be r alpha, right? For a finite rotation, I'll just label it over here. this distance throughout would be r multiplied by the angle, r alpha. So at intermediate rotation by an alpha, the distance moved would be r multiplied by alpha. But then you are only interested to find out the distance of this corresponding point, which is this distance. So what we have to do is we have to subtract from this r alpha this distance, which is nothing but, if you consider this to be the right angle triangle, this distance would be r sine alpha. So your trajectory would look something like xi would be xi plus r alpha minus r sine alpha. Or I can write x of t as xi plus, if I take r outside, then it'll be like alpha minus sine alpha. But then there is one issue, for trajectory, we have to express everything in terms of time. We have to express everything in terms of time, but we don't have any time variable in this equation. We only have everything. We have only expressed everything in terms of alpha. So how do we convert this alpha into, or how do we map this alpha or this rotation parameter with respect to time? So that we have to think. So for alpha for time, for any generic or intermediate time t, the circle rotates by an amount alpha. But for one full revolution, or for 2 pi radians of revolution, the that will be your end time tf, right? So the termination time of your trajectory would be after once the circle rolls one full revolution, right? So if your initial time is t0, after one full revolution of the circle, you will have this final time. So this is basically a direct proportionality relation, right? At intermediate time, the rotation would be alpha. At final time, your rotation would be one full rotation. That will be 2 pi radians. So from here, alpha would be 2 pi multiplied by t by tf. So if I substitute that over here for alpha, it will be like x of t would be xi plus r multiplied by 2 pi t by tf minus sine of 2 pi t by tf. That'll be one more stage. And in the final equation, we also have to substitute this r by, for one full rotation, if you begin with an initial position xi, and if you end with the final position xf, the distance between xi and xf is nothing but one full rotation of the cycloid, which is nothing but 2 pi r. The distance would be nothing but 2 pi r units, right? As it begins from xi and as it moves, as it reaches xf, that entire distance is nothing but 2 pi r, one full rotation of the circle. So from here, xf minus x0 is nothing but 2 pi r. So in that regard, r would be xf minus x0 by 2 pi. So if I substitute this into this expression, I'll get the final equation, the trajectory generation as per the cycloidal motion as x of t would be xi, initial position, plus xf minus xi by 2 pi. This entire term would multiply 2 pi t by tf minus sine 2 pi t by tf. So this final equation would be the governing equation of a trajectory that basically emulates a cycloidal motion. So that the cycloidal motion is also very smooth, right? As you can see, the locus of all the points would be something like this. It's basically very smooth, right? And due to the fact that we have sine terms inside it, the derivative would be cos. If you take a derivative further, it'll again be sine and cos terms. So in that regard, the position is smooth. Velocities would also be smooth. Acceleration would also be smooth. Just like a sine or a cosine curve. It'll be very smooth. All right. So that's about cycloidal motion, and the profile would look something like this. The position, velocity, acceleration profiles would look like this. If you simply plot this equation on a curve with time as a independent variable and x as a dependent variable, you will get this equation. You will get this curve, which is very smooth. And as I was saying earlier, since it has sine and cos terms, the velocities would be smooth, and acceleration similarly would also be very smooth because it only has sine and cos terms. So the derivative and double derivative would also be smooth, just like the position profiles. All right, so that's about trajectory, and few more points on how to implement this trajectory schemes. There are two schemes that we can basically have. If you want to deploy this trajectory, you can deploy that either in terms of either joint space variables. You can generate a trajectory as x of t. Sorry, you can generate it as x of t, x dot of t, or x double dot of t. Then if you have one more task space variables, you can generate y of t, y dot of t, and then y double dot of t. You can generate trajectory in a task space scheme, or you can generate a trajectory in joint space scheme. Maybe if you have an RR robot, you can generate theta 1 of t, theta 1 dot of t, theta 2, theta 1 dot of t, theta 1 double dot of t, and then theta 2 of t, theta 2 dot of t, and theta 2 double dot of t. So either of these schemes, you can basically, derive the trajectory. So again, depending upon what scheme you are choosing, it will have different implications or different effects on how the robotic arm would move. So let's see, how it basically looks like. So in joint space scheme, the time history of single or multiple actuated joints are being generated, using any of the schemes that we have considered earlier. So depending upon the boundary condition, maybe initial position, initial velocities, final position, and final velocity, you can basically create a time history of single or multiple joints. If your robot has single joint, you only need to generate a single trajectory for that. Or if your robot has multiple joints, such as an RR robot, you will have to generate multiple trajectories. And essentially, you can implement any of the schemes. You can implement a straight line, cubic, quintic, cycloidal, or even the case with parabolic blends. So joint space schemes are useful if a joint or a group of joints are to be moved. So like if your robot has joints, or if it has multiple joints, you can plan trajectory for all these individual joints, and then plan the trajectory planning. So maybe one example I can give you is, if you have an RR manipulator, something like this is X0, this is Y0, and this is your initial position of your RR manipulator. I'll maybe label this as Xi and Yi. And your initial angle, initial joint variables would be maybe theta 1 and theta 2. And you want your RR manipulator to move to a final position, maybe something like this. So I label, okay. So the joint variables, I label it as theta 1i and theta 2i for initial. And the final coordinates would look something like maybe theta 1f and theta 2f. And your final position would be xf and yf. So you want your robotic manipulator to move from xi, yi to xf, yf. So to plan the trajectory in task space, what you do is from xi, yi, you perform the inverse kinematics. Then you find out theta 1i and theta 2i. And then from the final position, from xf, yf, you again perform the inverse kinematics. And then you find out theta 1f and theta 2f. So now you have the boundary conditions, theta 1i and theta 1f. For the first joint, you have the boundary conditions to be theta 2i and theta 2f for the second joint. You can consider velocity boundary conditions if you are planning a third order trajectory or a cubic trajectory. Apart from position and velocity boundary conditions, you can also consider acceleration boundary conditions if you are planning quintic trajectory. So depending upon your boundary conditions, you can either decide to go for a third order or a fifth order trajectory, and then you plan trajectory. You plan a trajectory between these two joint variables. So that's how you plan trajectory in a joint space scheme, right? You begin with task space variables, initial and final. You perform the inverse kinematics. You obtain the initial positions of both of the joint variables. You obtain the final position of all the joint variables. Then you do the trajectory planning so that you will be getting the intermediate all the intermediate positions as a function of time. So between these initial and final positions, your manipulator arm would, move through a series of intermediate positions, something like this. Maybe the first position would be like this, second would be like this, third would be like this. Eventually, it will come to the final position, depending upon how you plan the trajectory. So that's how you plan trajectory in joint space scheme. In task space scheme, the time history of position and orientation of the end effector would be generated directly in task space itself. So instead of doing this, inverse kinematics, this extra step of inverse kinematics, you begin with xi, you begin with yi, you end with xf, you end with yf. And between these two conditions, you plan a trajectory, and between the y variable, you also plan a trajectory. Right? So you generate a set of x points, xi, then all the intermediate points, then you set xf. Then you plan a y trajectory for yi, then all the intermediate points, and then yf. And then what you do is you do the inverse kinematics for all these points, the start and intermediate points, find the joint variables, and then plug it into the motors as inputs. So the position you do or the stage at which you perform this inverse kinematics is different. for joint space and task space schemes. So in terms of task space, it is more natural for the robot operator to specify, right? Because we can basically see how the robot would move because we perceive everything in Cartesian coordinates. Because it's easier for us to predict the position of a robot if xi and yi are given, rather than giving theta 1 and theta 2. So like if someone is giving us theta 1 and theta 2, we probably won't know how that position would look like, right? But if someone gives you this xi and yi coordinates, we can immediately know the robot would be right at that coordinates xi and yi. So in that regard, it will be more easier, or it will be more easier for us to visualize for the robot. So in that regard, it's more intuitive for us to plan trajectory in task space. But then there are issues. There are difficulty in planning orientations due to representation issues. In this case, we can easily plan trajectory in Cartesian coordinates, but when it comes to orientation coordinates, that becomes slightly more trickier. Yeah, then there are other schemes. For task space, you can either use a linear interpolation or you can either use a circular interpolation. So what this essentially says, you can, if you have two variables, maybe xi and yi, you can do, you can probably plan the xi trajectory using any of your preferred scheme, something like maybe cubic, quintic, cycloidal, so on and so forth, etc. Whatever your choice of preference, and you can actually make yi follow xi using a linear interpolation or a circular interpolation. It does not really have to be completely independent. You can, for instance, in case of a circular arc, once you have obtained, once you have planned the trajectory for xi, yi can be as per this relation, x square plus y square would be r square. If you want your robot, uh, to start from an initial position xi, and you want your robot, sorry, initial coordinates would be xi yi, final coordinates would be xf comma yf. You essentially plan the trajectory of a robot only in x coordinates, maybe as per a quintic trajectory. You do that, but then you obtain the trajectory of y using this expression: x square plus y square is r square, and y would be r square minus x square under root, so that your robotic arm would move something like an r, like a curve, whose radius would be dependent upon this value r. Either you can do that, or you can do this linear interpolation, like a straight line, where x would be following maybe a cubic or a quintic trajectory, but xy would be probably following a straight line. But it'll gradually, just like a cubic trajectory, it will gradually start from zero acceleration, zero velocity, gradually increase, and then gradually close down. So like depending upon your preference, you can either use linear interpolation or circular arcs. If you're employing this task space scheme. I think in one of the lecture videos, the professor himself has demonstrated in MATLAB on how to implement this linear scheme, as well as this the circular arc scheme. So if you want more clarity, I would advise you to visit those two MATLAB simulations, which will probably give you more clarity on that. So task space, again, as I was saying, it's a bit trickier compared to this joint space, due to the fact that task space trajectory if you plan trajectory in task space, it may try to take your robot manipulator outside the workspace. Maybe, for example, in case of this RR robot, something like this. If the length of the RR robot, if the length of the RR robot, if you consider this link to be L1, and if this length to be L2, and if L1 is not equal to L2, the workspace would look like a donut. It'll have an outer boundary and it'll have an inner boundary. The workspace would look like a donut. DONO, look like a donut. Because if you one extreme of the workspace is when you fully extend the robotic arm. So maybe this would be the first link. This would be the second link. So this entire boundary is when you try to fully extend your manipulator arm. And this inner boundary would be when you try to fold your manipulator arm. So the first link would be L1 like this. Second link would be somewhere around here, L2. And because of the length difference, this is the innermost point the robotic arm can reach when it is fully folded. So the workspace now is between these two boundaries. And any point outside this boundary or inside this boundary would not be achieved, cannot be achieved by this RR manipulator. So if you plan a straight line trajectory between this initial position and this final position, if you try to plan a straight line interpolation, something like this, once the robot reaches this point, it tries to go out of the boundary. It tries to go out of this boundary. And all these intermediate points would not be accessible by the robot. So in that regard, the task space trajectory with non-reachable points would be an issue, when you try to plan trajectory in task space. So what you can do is from x0 and y0, do the inverse kinematics, you obtain theta 1i and theta 2i. And from xf and yf, you again do the inverse kinematics and obtain theta 1f and theta 2f. And maybe you can do a straight line trajectory between, these coordinates, theta 1i, instead of x0, y0, xf, yf, you can do a straight line interpolation between theta 1i and theta 1i and theta 1f, theta 2 and theta 2f. So your trajectory would, in task space, the trajectory would look something like a curve, so that it won't go outside this boundary. So yeah, that's one of the potential problems that you can have if you try to plan a trajectory in task space. The second problem is the task space trajectory will try to go near singular points. We have already seen what is a singularity and in what all configurations a singularity occurs. Specifically in case of an RR robot. So in case of an RR robot, singularity occurs when the link is fully extended like this, or when it is fully folded like this. First link first link over here, second link over here. Fully folded configuration also, the singularity occurs. So in this case, if you have an initial location and if you have a final location, and if you try to plan a straight line trajectory, at this point, at this particular point, your robot would be in a fully folded configuration. And that essentially becomes a singularity. And we have already seen the case of singularity that it basically loses a degree of freedom. It will have infinite velocity in one of the joints that will have probably a lot of adverse effects when you try to control it. So it will try to force the robotic manipulator to go through a singularity when you try to plan a trajectory in task space. Another case is when possibilities of ending the with other inverse kinematic solution, right? So if you consider this case, we begin with x0, y0, and you end up with this xf by f. So ideally, we begin with this configuration, right? We begin with this sort of configuration. Maybe we can call this an elbow down configuration. Ideally, it should have the final position should have ended up in a configuration something like this. It should have ended up in a configuration like this. Sorry, something like this, right? You could have simply rotated this entire manipulator arm in the clockwise sense so that it would have reached in this configuration. But instead, if you try to plan a trajectory like this, like a straight line, it basically switched the configuration from this elbow down configuration to this elbow up configuration. Instead of going through this configuration, it basically reached a configuration like this. So sometimes that may not be advantageous, right? Because imagine if you have an obstacle over here, right? In that case, you can only use this configuration. To reach this final position, you can only use this configuration. But due to the fact that you planned a trajectory in task space, you planned a straight line trajectory in task space, the robot would move along the straight line, which would end up in flipping its configuration, right? For example, if you try to have a straight line over here, so somewhere around here at the middle, the robot will have a singularity, right? At this point, the robot would be fully folded. So from here to here, it will be in one configuration. And once it moves away from this folded position, it can either fold down or it can either fold up. It's very difficult to predict which direction that robot is going to move. Especially in real situations, it's not that straightforward. It depends upon a lot of cases. Depends on the inertia, depends on the momentum. So it can either flip in from that singularity configuration. It can either flip into this uh, underarm position, or it can flip to this overarm position. It's very uncertain. So again, that is also one of the complications that we may encounter, when we try to plan a trajectory in task space. Right. So I hope that is we have covered all the basics or all the topics that we have solved uh, yeah, during this lecture. Now let's solve some sample problems. Uh, so for question one, it's a true or false question. The specification of robot's position and orientation as a function of time is called a path. Would that be true or false?
False.
That's false. We have been talking all this time for something called trajectory, but the question says it's path. So obviously that is false. The correct answer would have been trajectory. So that's fairly straightforward. Question number two, for a cubic trajectory planning, the acceleration profile may contain discontinuities across the via points if via point velocities are specified. So would that be true or would that be false? We have seen this case earlier, when via point velocities are specified. And when via point velocities are not specified. So which of these scenarios will have more likelihood of having discontinuous acceleration profiles? Is it the case when via point velocities are specified or when via point velocities are not specified? I mean, if the velocities are not specified, what are we doing? What essentially are we trying to do? In case when the via point velocities are not specified, the initial velocity of the next segment of the next segment would be the final velocity of the new segment of the previous segment. Right? So we basically enforce this constraint. When the velocities are not specified, we essentially enforce this constraint. Like if you move from one segment to the other segment, for example, if you have an initial position, you have a final position, and then you have a via point xv1, then you have xv2. So you will have this boundary condition, xi and xi dot would be specified. Xv is specified. If xv dot is not specified, we enforce one constraint that x the final velocity of the first segment would be considered as the initial velocity of the second segment. We enforce that constraint. And final velocity of the second segment would be the initial velocity of the third segment. So if we enforce that constraint, is it more likely to find discontinuities in acceleration or less likely to find discontinuities in acceleration? What could be the case? I mean, I can go back through the slides if more clarification is required. But in that case, the answer would be, the first case, when the via point velocities are specified, this is more likely to have discontinuities in acceleration. So here we are essentially splicing the velocities of the previous segment to the next segment. Due to that additional constraint, we are trying to smoothen out the velocities. And if the velocities are always smoothened, acceleration would also be more likely to be more smooth. But there, we are randomly specifying velocities however we want. So there can be discontinuities within the velocity itself. So due to that fact, it will get even more worse in case of accelerations. So when via point velocities are specified, you are more likely to find discontinuities in acceleration. So if further clarification is required, I can go back to the corresponding slide and I can explain. But in this case, the correct answer would be true, I believe. For cubic trajectory planning, acceleration profile may contain discontinuities if via point velocities are specified. So that is true, because it essentially agrees with this statement. So that is indeed true. Let me know if any further clarification is required. I can go back. Okay, so now moving on to question 3. If we define a variable u as t by tf, then the cubic polynomial function can be rewritten in a nested form as. we basically know how this cubic polynomial expression would look like. I hope you have seen this topic during the lectures, posted in the NPTEL itself. Let's discuss that somewhat more. For a cubic trajectory, x of t as a0 plus a1t plus a2t square plus a3t cube. If you consider your initial position x of t equal to 0 as x0 and your initial velocity x dot at t equal to 0 as 0, initial velocity as 0, and your final position x at t equal to tf as xf, and your final velocity x dot at t equal to tf as 0, the expression for this coefficients can be determined, and you can rewrite this expression for the trajectory of the variable x as x of t as x0 plus 3 by tf square xf minus x0 t square minus 2 by tf cube xf minus x0 multiplied by t cube. This would be how your cubic trajectory would look like in terms of the boundary conditions. So the problem with this expression is that if your time for your trajectory is very high, very large, these terms, tf square and tf cube would be even larger, and as a consequence, these terms would basically tend to zero. They would basically tend to zero, and you would probably get not very good representation. So in that regard, what you do is you basically normalize your time using this substitution u as t by tf. So at 0, your u variable would be 0, and at t equals tf, u would be 1. So you are essentially normalizing your time from 0 to tf into 0 to 1. So in that regard, you can actually write your trajectory in terms of this new time coordinate u as x of t would be, now the coefficients would be different, b0 plus b1u plus b2u square plus b3u cube. And similarly, using the corresponding boundary conditions, you can obtain this b0, b1, b2, and b3. Again, you can also write this expression in a nested form as b0 plus u multiplied by b1 plus u multiplied by b2 plus u multiplied by b3, something like this. So if you expand this out, you will end up with this generic expression. And the reason of writing it like this is because in total, you will only have 3 multiplications and 3 additions. So here you have 1 multiplication, you have 1 addition, and then if you multiply it with u, you have 2 multiplication and 1 addition. And if you do this addition, you will have 2 addition and 2 multiplication. And with this u, you have 3 multiplication and 2 addition. And finally, with this b, you have 3 addition and 3 multiplication. So writing something like this in a nested form would be much more computationally efficient than writing it in this manner. Here you require 3 multiplications here itself. Sorry, 4 multiplications here, 1 addition here, then again 2 multiplication and 1 more multiplication. So several multiplications are required. So this implementation is much more efficient because it requires fewer number of multiplications and additions. So again, it's only a change of variable. Instead of writing it in terms of t, you write the trajectory in terms of u, so that this problem would not arise. So in that regard, I believe the correct answer, if you substitute u instead of t by tf, your new trajectory would look something like, I believe it's option this one, the fifth option. Yeah, it's not x of t, it's basically x of u, actually. Yeah, it would basically be the fifth option. All right, that is indeed the correct answer. Now, moving on to question 4. This is a numerical problem. So the question gives your initial position is theta I is given as 30 degrees and theta F is given as 60 degrees. Initial and final velocities are zero. It's considered to be zero. So theta I dot would be 0 and theta F dot, that would also be 0. And the total trajectory is generated for 6 seconds. So the duration of the trajectory is 6 seconds. So what will be the maximum velocity of the trajectory if cubic polynomial is used? So theta dot max. This is what the question asks. That too for a cubic trajectory. So let's write the generic equation for a cubic trajectory. So theta of t would be a0 plus a1t plus a2t square plus a3t cube. And if I take the derivative of this theta dot of t, this would be a1 plus 2a2t plus 3a3t square. So if I substitute these boundary conditions into these two generic expressions, for the initial time, you will get 30 would be, if I substitute t equal to 0, I'll get it as a0. And for the initial velocity, I'll get it as 0 would be a1. And for the final position, it will be 60 would be a0 plus a1 tf plus a2 tf square plus a3 tf cube. And final velocity would be 0 would be a1 plus 2a2 tf plus 3a3 tf square. So I can write this as a matrix and vector form. So the unknowns are the coefficients. Unknowns are a0, a1, a2, a3. The boundary conditions on the other side of the equality are 30, 0, 60, 0. And the coefficient matrix would look something like 1, 0, 0, 0, then 0, 1, 0, 0, then 1 TF, TF square, TF cube, then 0, 1, 2 TF, 3 TF square. So we know TF is 6 seconds. And if you substitute the value of TF into this matrix, I'll call this matrix as A and this coefficient matrix as B, you will obtain A0, A1, A2, A3 as, by inverting this A matrix and multiplying it with B. So if you do that, I think you will get the value of A as A0 is obviously 30, right? From this equation, it's all obviously 30. A0 is 30. And from this equation, A1 is 0. And A2, you will get some value. I think it's probably maybe around 2.5 or something. And A3 would be a very small value, minus 2.27, maybe something like that. So now you can write this generic equation of trajectory as 30 plus 2.5 t square minus 0.27 t cube. That will be your expression for the position. And then velocity would look something like a1 is a1 is 0. Now you have 2 a2t, so 2 multiplied by 2.5 t minus 3 multiplied by 0.27 t square. This would be your theta dot t. So if you recall the profile of a cubic polynomial, you will have the position varying something like this. This will be your theta of t. And over here, you will have your time axis. And your velocity profile would look something like this. Right? And it's basically obvious that the maximum velocity occurs at time t equal to tf by 2. So if you substitute tf by 2, which is 6 by 2, which is 3 seconds into this equation, into the equation of theta dot of t, you will be able to get the correct answer in that case. Right? So if you substitute into this equation, 2 multiplied by 2.5 multiplied by 3 minus 3 multiplied by 0.27 multiplied by 3 square, you will get the answer to be around 7.49 something. That'll be your final answer. That'll be your peak velocity or the maximum velocity, and your answer will be 7.5 or in that region. So I hope that is clear. It's a lengthy process. First, what you have to do is from the given boundary conditions, you have to find out the coefficients. Then using the coefficients, you substitute that into the generic equations of velocities. And if you know at what time the maximum velocity occurs, you substitute that time into this velocity equation, and the corresponding value you will be getting would be the value for maximum acceleration. So that is indeed the answer. I hope that is clear enough. So the answer is indeed 7.5. Now, moving on to question 5. A third order trajectory planner has control over initial and final accelerations. Is it true or false? Does anyone want to answer that? A third order trajectory planner has control over initial and final accelerations. Theta of t as a0 plus a1t plus a2t square plus a3 t cube. Can we really control the accelerations uh, with just 4 boundary conditions? Would that be possible or not? It won't be possible, right? Because we only have 4 coefficients. So to have a fully determinate system of equations, we can only have 4 boundary conditions. So we have 2 boundary conditions for initial position and velocity, right? We have boundary conditions for initial position initial velocity, then final position, and final velocities. So in essence, we can only control initial position, initial velocity, final position, and final velocity. We can choose the boundary conditions to our liking. So since we only have four parameters or these four coefficients, we can only have control over these four boundary conditions. But if you are using a quintic polynomial, theta of t as a0 plus a1t plus a2t square plus a3t cube plus a4t to the power 4 plus a5t to the power 5, we have six coefficients: 1, 2, 3, 4, 5, 6. So to have a fully indeterminate system of equations, we can have three initial conditions and three final conditions, right? We can have control over initial position, velocity, and acceleration. We can also have control over final position, velocity, and acceleration if we are using a quintic polynomial. But for a cubic polynomial, we don't have control over accelerations. So in that regard, the answer here would be false. So I hope that is clear enough. If any further clarification is required, please let me know. So the answer is indeed false. All right. So moving on to a question. This is similar to what we have solved, but I feel this is more easier. For any given single rotary link manipulator, the initial joint position is given as 20. So theta I is given as 20. And the final joint position, theta F, is given as 60 degrees. And the final position is reached in 10 seconds. So TF is considered to be 10 seconds. The motion is supposed to be in third order polynomial. We can also consider the final and initial velocities to be zero. So theta I dot is zero, theta F dot is zero. Then the joint position can be written as. So again, this is exactly similar to what we have seen earlier. We can write the coefficient matrix directly as 1, 0, 0, 0, 0, 1, 0, 0. Then 1 TF square, TF cube, then 0, 1, 2 TF, 3 TF square. Then over here we have A0, A1, A2, A3. And over the other side of the equality, we have 20, 0, 60, 0. And we know TF is 10 seconds. So if you substitute everything into this A matrix, and this is maybe this unknown X matrix, and you can consider this to be the B matrix. And if you invert this A matrix and multiply it with this B matrix, you will get your matrix of your vector of coefficients. And you will end up with A0 as 20, A1 as 0, A2 would be probably, I think, 1.2, and A3 would be minus 0.08. So in that regard, the correct answer would be option. This is how you would do it. The final answer, you will basically get the vector that you obtain from this A inverse B. The corresponding values inside that vector would be your the components A0, A1, A2, and A3. It's a you only have to multiply that matrix and invert the matrix and multiply that with this vector of boundary conditions. So that's question 6. I think the correct option is this fifth option, actually, not the fourth option. Moving on to question 7, a fourth order trajectory planning can satisfy initial and final conditions of position, velocity, and acceleration. A fourth order, would that be true? So in all cases, we were considering a polynomial with odd number of a degree of odd number. It's either third order or it's either fifth order. What about fourth order? A fourth order polynomial would look something like this. Theta of t would be a0 plus a1t plus a2t square plus a3t cube plus a4t to the power 4. So how many constants do we have? We have 1, 2, 3, 4, 5. So to determine these 5 constants, we need 5 equations. 5 boundary conditions. But the question says, would it be possible to satisfy the initial and final constraints on position, velocity, and accelerations? Can we satisfy 6 constraints using 5 equations? That is obviously not possible, right? So in that regard, the answer is also false, because to satisfy these 6 constraints, uh, uh, the boundary conditions of position, velocity, and acceleration at the initial and final positions, we need at least a quintic polynomial. We need a polynomial of degree 5. But we are trying to do the same thing with the fourth order polynomial. So a fourth order polynomial can only satisfy at the max 5 constraints, right? Because we only have 5 coefficients here. So to solve it, we only need 5 equations or 5 boundary conditions. We cannot satisfy a sixth constraint. So in that regard, the option is false for question 7. Yeah, it's indeed false. For question 8, this is a cycloidal motion problem. Let's see how to target this. For a single rotary link manipulator, the initial joint position xi is given as 20 degrees and the final joint position xf is given as 60 degrees, and it reached the final position in 10 seconds. So TF would be 10 seconds. The motion is supposed to be cycloidal, in cycloidal motion. Then what will be the maximum joint velocity? So like from earlier, we know that the trajectory, the governing equation for a cycloidal trajectory is given as xi plus xf minus x0 by 2 pi multiplied by 2 pi t by tf minus sine of 2 pi t by tf. We have derived this earlier. So to find the velocity, if you take the derivative of this, x dot of t, or maybe I'll rather multiply this out, x of t would be xi plus xf minus x0 by 2 pi multiplied by 2 pi t by tf minus xf minus x0 by 2 pi multiplied by sine of 2 pi t by tf. So if I take the derivative of this, derivative with respect to time, the velocity x dot of t would look something like xf minus x0 by 2 pi multiplied by 2 pi by tf multiply minus xf minus x0 by 2 pi multiplied by cos 2 pi t by tf multiplied by 2 pi by tf. So if I take these common terms, xf minus x0 multiplied by 2 pi by tf, we have this term over here. The same term is also over here. I'll take the common terms outside. xf minus x0 by 2 pi multiplied by 2 pi by tf whole multiplied by 1 minus cos of 2 pi t by tf. This will be the expression of velocity x dot of t. So naturally, just like what we have seen in the previous case, if you have a quintic polynomial, something like this, velocity profile would look something like this, and the maximum velocity would be at time t equal to tf by 2, right? Maximum velocity will always be at at the middle, at the midpoint of the trajectory. From that point onwards, it starts to decelerate. It tries to slow down until it reaches uh, the end point. If you are really unsure if that is not correct, whether it is correct or not, you can take the derivative of the velocity, equate it to zero, and find the time, find that corresponding time. If you want to take the maximum time, dou x or find t from dx dot of t by dt equal to 0. If you solve this equation, you will definitely get the value of time t as tf by 2. This is where your maximum velocity would occur, right? Because at maximum velocity, if this is the velocity profile, at maximum velocity, the slope of velocity would be 0, right? So that's what we are trying to find. We are trying to find the slope of, we are trying to find the location of time where the slope of velocity is 0, and that corresponding time, that time would correspond to the location of maximum velocity. So if you do this, you will obtain the time as tf by 2. And if you substitute tf by 2 into the expression here, you will get it as x dot at tf by 2 would be xf minus x0 by 2 pi into 2 pi by tf multiplied by 1 minus cos of 2 pi by tf multiplied by tf by 2. So this tf and this tf will get cancelled. This will also get cancelled. So you'll end up with cos pi. So cos pi is minus 1. So the term inside this bracket would now become 2. So you'll end up with xf minus x0 by 2 pi multiplied by 2 pi by tf multiplied by 2. So this 2 and 2 will get cancelled. This pi and pi will get cancelled. In the end, you will end up with xf minus x0 by tf. You'll also have one more 2 from here, I think. I hope the answer is 2 multiplied by xf is 60, x0 is 20, tf is 10 seconds. So your answer is 8, I believe. Maximum velocity would be 8 degrees per second. So I think the answer is option B. I hope that is clear enough. Yeah, the option is indeed answer B. Moving on to question 9, the desired trajectory of the joint manipulator should be once differentiable. No, it should be at least twice differential, right? Because uh, yeah, it should be at least twice differential. Otherwise, you won't. You will get. Uh, how can I say that? If you cannot differentiate it twice, you won't get any accelerations. Because if your trajectory is linear, if you differentiate it once, you will get constant, and if you again further differentiate, you will get zero. So it has to be at least twice differentiable for the in order for you to execute a trajectory. So in that regard, this option is false. You need at least twice differentiable. Yeah, uh, it should be at least twice differentiable. Question 10. The best trajectory between 2 points is based on straight line interpolation in terms of smoothness. Best trajectory between 2 points is based on straight line. No. We have seen that cubic, quintic, and cycloidal, and even straight line with parabolic blends, they are far superior than a simple straight line interpolation, right? Because straight line interpolation will have infinite accelerations at the very beginning and at the very end. So we can all agree that to be false as well. There are far superior trajectories compared to straight line interpolation. Yeah, as I was saying, constant velocity, straight line interpolation will cause infinite acceleration and deceleration at initial and final stages. So that is not something that we really want inside our trajectory. The second last question, in a 2D space, xt is generated based on smooth trajectory schemes, then what will be yt based on a straight line interpolation? So we have seen this earlier. This is a task space or trajectory planning in task space, where you basically generate x of t maybe as a cubic polynomial or a quintic polynomial as per your convenience or as per your preference. That will be a0 plus a1t plus a2t square plus a3tq, and uh, the uh, other variable or the other coordinate, the question asks you to determine the other variable, the second variable, based on a straight line interpolation. So you basically know the straight line equation is y minus y0 would be y2 minus y1 by x2 minus x1 multiplied by x minus x0. Or in this given instance, I'll bring this y0 to the other side plus y0. Uh, okay. Yeah. So instead of 2 and 1, I can actually replace it with initial and final you know uh, terms. So y of t would look something like yf minus y0 by xf minus x0 multiplied by x minus uh, xf or x0. Either case, it's still rather valid. Plus, instead of y0, I took it as yf. So for every x, this will be x of t actually. So for every x in x of t, you can get a y of t using this straight line interpolation. If you are doing the circular interpolation, y of t would look something like r square minus x of t square, under root r square. This is for straight line interpolation. This is for circular interpolation. And these are two examples of trajectory planning in task space. And I believe the correct answer in this case would be option B, I guess. Yeah, option B. That's my final answer. Yeah, that's indeed correct. Moving on to the final question. Choose the correct statements. Straight line interpolation has constant velocity throughout from the start of the interpolation to the end of the interpolation. So we basically know that if you have initial position and if you have final position, if this is the straight line, velocity, if you take the derivative, velocity would essentially be a constant, something like this. So the first statement is indeed true. Second statement, straight line interpolation has constant non-zero acceleration throughout, but with instantaneous infinite accelerations at the beginning and at the end of the path. So for straight line, we already know that we have a constant velocity. So the derivative of a constant velocity would be zero acceleration, right? So acceleration will be zero actually throughout. This will be your acceleration. But then due to the fact that there is an instantaneous velocity at the very beginning, it will have instantaneous infinite acceleration and instantaneous infinite deceleration at the very end. But everywhere else, the acceleration is zero, not non-zero acceleration. So that is false. Statement 3, straight line interpolation has zero acceleration throughout, but with an instantaneous infinite acceleration at the beginning and at the end of the path segment. So that is true, what we have just discussed. For this, a quadratic polynomial can satisfy position and velocity constraints at the start and at the end of the path segment. So quadratic polynomial would look something like this. Theta of t would be a0 plus a1t plus a2t square. So here we only have three coefficients. So it can only satisfy three boundary conditions. But if you want to satisfy position and velocity at beginning and at the end, you require four equations. But here you can only have three boundary conditions. So that is also false. With quadratic, you cannot satisfy uh, position and velocity constraints. For that, you need at least a cubic polynomial. What we have seen earlier. So this is false. The fifth one is a quintic polynomial can satisfy position, velocity, and acceleration constraints at start and endpoint. So that's true. We have discussed this already. So the correct statements are option 1 is true, option 3 is true, option 5 is also true. So I think out of all these options, the final option, F, is the correct answer. Yeah, so that is indeed the correct answer. Yeah, so with this, I would like to wind up this session. We have solved the problems and we have discussed on the topic of trajectory planning. So unless there are any further questions, I would like to wrap up this session. Would there be any questions?
Well, For
Yeah.
trajectory in the drones, so this task space only used, sir.
In drones, I'm not sure because, yeah, maybe probably drones you would plan it in that task space, but then I don't think you have any joint coordinates in drones, right? I don't know how drones are modeled kinematically. Most likely, you will have six coordinates. You will have X, Y, Z, and you will have three orientations as well. So yeah, probably it'll be planned in task space itself, but I'm not sure. I haven't worked with drone kinematics, but I believe the obvious answer seems like that. Plan it in task space. In robotic manipulators, like we have joint
Okay,
variables
okay, sir.
and task variables, so that's why we need to consider on which variable we have to plan it. Okay.
Okay, sir. Okay.
Okay. So yeah, thank you. If there are no more questions, thanks for joining. It has been a long session. So yeah, we'll meet during the next week's live session. Okay, then see you then. Thank you. Thank you for joining. I shall stop.